Hello and welcome to this EE328 lecture video on ideal sampling and the Nyquist theorem. We are going to talk about ideal sampling, and that is the bridge between continuous time signals and discrete time signals. That is, we sample a continuous time signal to turn it into a discrete time signal. The opposite of that process is called reconstruction. So if you want to take a discrete time signal and create a continuous time signal out of it, you are then reconstructing the signal. In this class, we are going to focus exclusively on regular sampling. This is also sometimes called uniform sampling, but the idea is that the time axis is going to be chopped up into uniform or regular intervals. And so I label these intervals as having width t sub s, or the sampling time, and they go in both directions. So we're going to take the continuum, that is the continuous time axis, and split it up into these discrete points spaced every ts seconds. And likewise, my notation for sampling frequency or sampling rate, I'm going to use f sub s. And that's just the reciprocal of the sampling period measured in samples per second. And of course, the reason that we're doing this is that most signals in the universe are continuous time. But in order to do things with them, recently, with digital computers, we need to discretize them. But we also want to sometimes store them or compress them. And so the motivation for this lecture is that to do anything in modern digital circuitry, you need a concept of a discrete time signal, but that signal likely came from a continuous time source. So it would be nice to know how to get from there to here. The fundamental question that underlies every kind of digital system is how frequently should we sample? This has tremendous implications for what kinds of processes the system will be faced with, but also what kinds of things you want the system to be able to do. And that can get kind of confusing. At the end of the day, really it's just going to boil down to, is what is lost important to me? So I hope you can see that in sampling a continuous time signal, things are lost. Like clearly, if I have any continuous time signal, pick your favorite one, this has a lot of information in it, right? It has a continuum of a domain, and it has a continuum of range, and there are all these points along here. All of that contains data, possibly information. But if I discretize it, if I say, you know what, I only want this, 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 I mean, clearly we are throwing away the information between the dots. And I think it's at this point an interesting point to make is that if I just handed you the dots, a priori you have no way of knowing that they came from the black curve or maybe the red curve. Right, so clearly if I just hand you the dots, then you can't tell, in this case, whether they came from the black curve or the red curve, which are two continuous time signals. So, and there's nothing we can do about that. It's a fact of life. The question I'm asking here is it important that they came from the black curve or the red curve? And that's going to be, the answer to that is going to be context dependent. Clearly, if I sample the black curve more frequently, if I decrease the sample time, then quote-unquote fewer continuous time curves would match the dots. So what we're seeing is this trade-off between accuracy, or more information, that is, make TS small, and size, basically, where the more you sample, the more data you have to deal with. And that can be a problem if you have limited storage. It can be a problem if you have limited time, because it takes more time to transmit or communicate or calculate if you have more data points. But it can also be a problem just in terms of price and how much it costs to sample very frequently. So if I want more info, I'd have to decrease the sample size. If I want less size, it's kind of a crude way to say it, then I would want to increase the sample time. And of course, sample time and sample rate are reciprocals, so you can also think of this as increasing sample rate, decreasing sample rate. So at this point, I think we have to start to try and remind ourselves a couple of facts about continuous time signals, because those facts will have implications about the answer to this question of how frequently we should sample. And the first fact I kind of want to remind you of is this duality between time and frequency. So I'm going to make a little chart here, and time will be, different categories in time will be the rows, different categories in frequency will be the columns. And so I want to split all possible signals up into these 4 quadrants. So these are continuous time signals. I want to differentiate those that have finite duration. That is, they only last for a finite amount of time, versus those that are infinite duration, i.e. those that go on forever, either left or right or both. And that same concept applies, or its dual applies in the frequency domain. But there we don't call them durations, we call them bandwidths. So this column will contain all those signals with finite bandwidths. And this column, all those with infinite bandwidth. So let's think of, and I hope you agree that this actually covers everything. Signals can either be finite or infinite duration. There's no third category in time. And, or I should say, signals can either be finite bandwidth or infinite bandwidth. There's no third path there either. So this carves up all possible signals into these nice 4 neat boxes. So let's take a look at a couple of examples that might fit into these boxes. So let's start here. Finite duration, infinite bandwidth. So I think the classic example, if I draw it in the time domain, is everyone's favorite rectangle function. Right? This is certainly finite duration. And this was one of the main examples that we leaned on in 228. The frequency domain version of the signal, or its Fourier transform, is a sinc function, which has no finite quote-unquote duration in the frequency domain, so we would call this an infinite bandwidth signal. Okay, so that's one example. There are many more. Let's do the other corner here. So this is finite bandwidth, but infinite duration. And here I want to do this one next because we want to capitalize on the time-frequency duality principle of Fourier transform. And that is, if in the time domain I come across a sinc function, then I know immediately that its Fourier transform will be a rectangle in the frequency domain. Okay, so I've just capitalized on duality to say I'm just going to flip these pictures around, and now all of a sudden I have an infinite duration time domain signal and a finite bandwidth frequency domain representation. Okay, so those are the kind of classic canonical examples. We also have plenty of examples that live down here in this bottom right corner. So I think my favorite example would be this signal, say an exponential, a one-sided exponential decay. And this signal in the frequency domain kind of has this kind of low passy image. Okay, so this has infinite duration. That is, it goes on and on forever. There is no point in positive time for which the signal is 0 forever after. And the same can be said in frequency. There's no frequency beyond which that frequency, the spectrum, is 0. Okay, so how about that upper left-hand box? And the reason I left it for last is because it is special. It is special because it is empty. There are no strictly finite duration signals that also have a strictly finite bandwidth. Okay, so this is one of the results that we had in 228, and it basically says you can't have it both ways. You can either be strictly finite duration, and then you get infinite bandwidth, or you can get a strictly finite bandwidth, but then you have to pay for it with infinite duration. There are these bottom right ones that are kind of like the worst of both worlds, but you can't have it both ways. You can approximate it, like, don't get me wrong. There are ways to maybe put a little bit of ripple down here in the time domain, and that will suck in the frequency domain. So there are approximations, but there are no truly finite duration and truly finite bandwidth signals. And that's going to become important in a moment. We've got a couple other concepts to review before we go into sampling, and that is this idea of an ideal filter. So remember, filters are characterized both by their magnitude and phase effects on inputs. And so if we talk about magnitude properties of ideal filters, they're going to have, in the frequency domain, a constant passband gain, so call it gain of A. And we're looking at the magnitude of h of f here. They're going to have 0 stop band gain, so in the stop band, they're going to be down here at 0. And an ideal filter has no transition band, and that is the band from high to low, or from pass to stop. So in an ideal filter, these are kind of also called brick wall filters. You're either in or you're out, and there's no shades of gray. But then also we can talk about the phase effects, which we have to look at the angle of the transfer function. And in an ideal filter, this is identically 0. Okay. An ideal filter does not affect the timing or the phase of its input signal. Okay. So what else can we say? Oh yeah, our old friend, the Dirac delta. So it has a couple of properties. There was the product property, or the sieving, or the sifting property, and then how it reacts in convolution. I want to focus on the first and the last of those. The product property merely says that if you multiply any signal with a Dirac delta, then you pick off the value of that signal at the point where the delta fired, and that then scales the delta function. Okay, so a lot of times this last part gets dropped off and people just think that it's left with x of t sub 0, and that's not true. So the picture that I have in my mind when I do this is I picture an arbitrary x function, and then I pick a delta function at some t naught, and then I also tend to draw the fact that that delta function is actually 0 everywhere else. And that helps me remember that when I multiply this by that, I get 0. When I multiply this by that, I get 0. And so at the end of the day, what I get is the delta just scaled up to whatever this value was. Okay, so when you multiply a delta by a function, you get a delta back. That delta is scaled by the value of the function at the point in time, or the point where the delta fired. The other important piece of information about deltas that we need for this lecture is that they act like ones when you convolve. So you might have learned this as x of t convolved with delta of t equals x of t, and that's true. I just want to point out that it doesn't actually matter what domain you're in. So here I've listed these as functions of frequency. That's fine. Convolution still acts the same, provided you have a one-dimensional domain. And I've also shifted the delta over. So this delta doesn't fire at 0, it fires at frequency f0, and the effect of that is that it's still a unity element. I still convolve x with delta and I get x, but I get x shifted. Shifted by how much? By the delta shift. And then lastly, something that you likely knew but may not have thought much about is that if I have two signals, and I find out that their continuous time Fourier transforms are the same. That's this abbreviation, sorry. This is continuous time Fourier transform, CTFT. If I have, so if little x in the time domain gets mapped by the Fourier transform to, say, big X, and some other time domain signal, call it x hat, also gets mapped with the Fourier transform to big X, then we say that little x and little x hat are equivalent. That's kind of a mathy way to say that they're equal, and I just want to point out that they're not technically necessarily equal. That is, x and x hat can vary on very small measures. What do I want to say here? So if I take this time domain function and I find that its Fourier transform is a sinc, and I take this function and I puncture a hole right there and I replace the function up there, if I Fourier transform this, I'll get the exact same thing, a sinc. And so I just want to say that in terms of engineering, this signal, say called little x, and this signal called little x hat, we should treat these the same in engineering, right? There is no physical effect that puncturing this at a single point and moving that function value, that cannot have any physical effect because in particular there's no energy in the difference between these signals. So that's the technical way, is that there's no energy x minus x hat. The energy in here will equal 0. And we say that in engineering, if the difference of two signals has no energy, then they are equivalent. As far as you're concerned, it's okay to say x and x hat are equal. In fact, that's what I'd like you to think, is that if two signals have the same continuous time Fourier transform, then they are, for all intents and purposes, the same signal. Okay, with all that out of the way, let's talk about ideal sampling. So I want to give you a bit of autonomy here. I would like you to picture in your head your favorite time domain signal, and we're going to call it x of t. I'll give you a second to fill in the slide with your best picture of your favorite time domain function. And we're going to represent sampling by this multiplication operation. That is, x of t is our continuous time kind of source signal. S of t is what's called an impulse train. And we'll see in a moment that if I multiply a signal with an impulse train, I will get another continuous time signal. But this is the sampled version of x. Okay, that's my claim. That's what I hope to show you by the end of this slide. Okay, so my favorite time domain signal might look like that. It goes positive, goes negative, finite duration, infinite duration, doesn't really matter at this point. And I'm telling you, I'm giving you freedom to pick x, but I'm telling you what s must be. S is this impulse train. And so this is an infinite sum where I'm adding a bunch of Dirac deltas, or impulses, in both positive and negative time. These deltas fire every t sub s seconds in both directions. Okay, so the way that I think of this is I pick my favorite little n index, usually 0, and I plug in that n equals 0, and I just get delta of t. So this is the n equals 0 case. But remember, this signal has 0 value everywhere else along the time axis. So if I add something else to it at a different time, that other thing doesn't know that this guy is firing at 0. So now pick your second favorite index, usually mine is n equals 1, and then I see this is a delta of t minus ts. So this is the n equals 1 term. And you can keep doing that until you get a feeling for what's going on. So we're adding individual deltas every t sub s seconds. Okay, so now what I'd like you to do is I'd like you to imagine what happens when I multiply the x of t signal with the s of t signal. And if you're thinking that sounds like an application of the product property of deltas, then you were paying attention. So what we get is scaled deltas. Each of them scaled by the x function at that point in time. So I'm just going to kind of give myself a guide here. This is roughly what my x function looked like. So I got these impulses centered every t sub s seconds, but now instead of being uniform height, they are of differing heights, and those heights correspond to the values of the x signal at that point in time. Okay, so to show you what's going on here, we're saying y of t is x of t times s of t, which means it's x of t times this infinite sum. And since there's no n's or anything in the x, we can bring it into the sum. And now we're going to do a bunch of product property rules. So this is then the infinite sum of x at nts times delta of t minus nts. And I do want to highlight that this is still a continuous time signal, right? It's still a function of little t. But the only information contained in this signal are the function values of x at these intervals nts. So this is how we think of the discrete time signal y of n as being the sampled version of the continuous time signal x of t. Okay? Because the only information contained in y of t is in the heights of the deltas. And so if you were to extract that information, then the only information included in here could be as well represented by this list of numbers rather than a continuous time function. So let's talk about everything that just happened, but do it in a different domain. This is actually going to be the easier domain. It's going to be hard for us to pick the exact Fourier transform of this signal because I just asked you to sketch it. So instead, we're just going to sketch a spectrum of this signal. I don't know if this is going to be truly a representation of what I had on the last slide, but let's make it symmetric. It technically doesn't have to be, but let's also, let's do something like that. Yours can look different. You are free to choose what your x of f looks like. The other curveball here is that if we multiply in the time domain, then that corresponds to convolving in the frequency domain. And the other thing that you need to know here is that if I specify s of t as the impulse train, then its Fourier transform, so this is a Fourier transform pair with s of t, and since s of t was the impulse train, s of f, and this is one of the coolest things about impulses, I think, is that its spectrum, its Fourier transform, is also a train of impulses. We can do a follow-up video on why that's true, but for now, I would like you to take it, or to acknowledge that the Fourier transform of an impulse train is this function here, a train of impulses in the frequency domain. So this is an impulse at f equals 0, an impulse at f equals fs, an impulse at 2fs, and likewise. However, these are all scaled by 1 over ts. So these are all fs high. Okay, and then let's give this, it has peak height a. So let's talk about convolving with impulses. That was the other reason that we reviewed Dirac deltas. So we know that big Y sub f is the convolution of x of f with s of f, which is an infinite sum of Dirac deltas. And since convolution is a distributed operator, or if you like, a linear operator, then the convolution of x with a sum is the sum of x convolved with every term in the sum. So this is fs times the sum over index k of x of f convolved with delta that fires at kfs. And here is where I'd like to apply that unity element of convolution property from 2 slides ago. This is a scaling factor fs times the sum of a whole bunch of x functions, but all of them shifted by integer multiples of fs. Okay. So if you're confused on that last step, go back a couple slides and review your knowledge of how delta acts in convolution. But the idea here is that this picture, this spectrum for y of f, is going to be the sum of scaled copies of x. And those copies are all shifted by different integer multiples of fs. Okay, so here is the first copy, which is just the one still centered at DC. Okay. So I haven't changed the shape too much, except I have changed the height. This is now of height a times fs. And now I go over 1 fs, and I draw the same picture again. Same height, a times fs. And then I do it again. Same height, a times fs. And I do it in both directions. Okay, so if you need help following along, this is the k equals 0 copy. This is the little k equals 1 copy. This is little k equals 2 copy. And little k equals negative 1 copy. And these go on and on forever. These are called the spectral copies of x of f. Clearly, x of f does not equal y of f, right? It has the same shape, but it's copied an infinite number of times in both directions. So that means y of t and x of t are different signals, and clearly they are. One is this continuous picture that I showed you before. The other is a bunch of impulse functions. But I also want you to see another thing, is that in what I drew here for y of f, it was important how wide my x of f picture went when I was drawing copies of it for y of f. Can you see that? That if I had been a little sloppier, if I had drawn something like that, which then leveled out, then all of a sudden the copy to the left would be kind of interfering with the copy to the right. And that is the essence of the Nyquist sampling theorem. So we'll get to that in a second, but I just want you to see that it mattered here, not so much the shape of x of f, but its width, right? So if we're talking about a baseband signal, which we are here, this is centered about DC, then I would call this the bandwidth of x. So B is this single-sided bandwidth. So that actually gets us to this slide where we talk about there are two possible situations. That once I take the spectral images and I copy them over and over again, that I get overlap, or I could have no overlap. So again, I'll do the kind of sloppy picture where here's the k equals 0 copy, and then the k equals 1 copy, and the k equals 2 copy, and then if you like also down here, where I've kind of drawn them as crossing each other, but really this is a sum, remember. So it would really look something like something like that, right? Where these two bits are adding up to do something kind of strange in the middle here, and then we get a single image. But then I'm adding things that are falling with things that are rising, and so I would get something nearly flat. And then go back to the regular image, and then again. And so what we get is we get something like this red curve for the spectrum. Whereas, if there's no overlap, we draw it nice and narrow, then I can add these all together and they don't interfere with each other, right? They all can kind of be treated separately. And the formal way to talk about reconstruction here would be, I need to do something to y to get back an estimate on x, or to get back a reconstructed version of x, which I'm going to call x hat. I think the most reasonable thing to do would be to try and filter, right? Because x is sitting right here in the center. So if we could just introduce a filter, it would have to be low pass, it would have to be ideal, because I don't want to do anything other than scale this back up, and it would have to be ideal because I want to perfectly reject all of this other stuff over here. But if I could do that, then after filtering, I would get this picture. And if I make the gain of the filter to be 1 over fs, then I can actually reconstruct this to be of height a, in which case the spectrum of x hat is equal to the spectrum of x, which we said we'd agree to call that x hat of t is a perfect reconstruction of x of t. Okay, so this is the best case scenario, that no information was lost. We made a lot of idealized assumptions, i.e. we used impulse functions, we used ideal low-pass filters, but at least mathematically, this is a way to reconstruct perfectly a signal that you have sampled and then unsampled, if you like. Contrast that with this overlap case. In the overlap case, there is no clear position that I should filter, right? There's no, because of this overlap, I don't know, should I put my filter there, my corner frequency there, or should I put it up here, or should I just stick to my guns and put it kind of dead center like I did over here? If I put it in any of those places, the picture I get will not be x of f. I want you to see that. So let's go with this. Let's say we use the same filter, and we just put the corner frequency halfway between 0 and fs. Then what we get is we get the right kind of middle bit, but then the high frequency components are off. Yeah, so the peak may still be up here at A, but the problem here is that we've got this high frequency stuff that wasn't present in the original signal. So we wanted that. And this gets a frowny face. So the reason that I highlight the difference between overlap and non-overlap is that in one case, in the no overlap case, reconstruction can be, in the ideal sense, be perfectly achieved. And in the overlap case, it's out of the question. There is no perfect reconstruction to be had. So, how do we guarantee that we live in the no overlap case? This ties it back to a design decision, or what sampling rate you should look for if you want to be able to lose as little information as possible, which is actually the gist of the Nyquist sampling theorem. And the Nyquist sampling theorem says, in a nutshell, that for perfect reconstruction to be possible after ideal sampling, the sampling rate that is chosen must be at least twice the highest frequency component of the signal to be sampled. So, a couple of things to note here. B is the bandwidth of the continuous time signal. And as long as the sample rate is more than twice that, so let's say B was here, and as long as Fs on the frequency axis is bigger than 2B, then we will have a gap because the next spectral image will be centered at Fs. And if it's spaced more than 2B away, then we're guaranteed a gap here. And any non-zero gap, I can squeeze a brick wall filter in between. So that's actually the other important thing here, is that this is a strict inequality. You cannot sample at exactly twice the bandwidth, or else you would get a little bit of overlap. And then the other thing to point out is that this number, twice the bandwidth, is often called the Nyquist frequency. Nyquist frequency of a signal. If I hand you a continuous time signal, that signal will have some bandwidth. It could be finite, it could be infinite. If you double that number, then you get the Nyquist frequency of that signal. That then tells you the lower bound that you would have to sample at if you were adamant about losing no information. Okay, so this is not the answer. I don't want to go through here and pretend that I'm giving you the be-all end-all answer to how to sample. It is a bound, and at this bound we know what would happen in this case. Right? Certainly sampling above this rate will increase the information that you retain, but I also want you to be realistic in seeing that many signals that you would like to deal with in continuous time don't have a finite bandwidth. And if you double something as infinite, you get infinite again. So that would tell you that you'd have to sample infinitely frequently to lose no information, which is a really complicated way of saying that for many signals with bandwidths that are quite large, approaching infinity, there is no way to sample them and not lose information. Okay, that's the main takeaway here. However, if you are ever presented with a signal with a finite bandwidth, then its Nyquist sampling rate will be finite, and that gives you the lower bound on your sampling system. All right. Thank you, and I will see you next time.